Hi, we are team number one, and today we are going to present our PIA. The integers of this team are, well, myself, Jesus, Sergio, Adrian, Danae, and Diego. Okay, so basically, the problem that we found about optimization was, I don't know, this is a problem of Minecraft uh, where you have 20 fences and you want to make the the fence that has the most amount of area, well, I don't know, to get more animals inside. So basically, well, you only have 20 fences and the shape has to be rectangular.
Now, the variables that we used for the project is L, which means length of the rectangle, and W means width of the rectangle, which are the variables needed to get the area of a rectangle, okay? And the perimeter restriction is an immovable limit, which means that in geometry, the perimeter, which is with variable P, of a rectangle which rectangle needs to have a base of x and height of y, is defined with the formula perimeter equals 2 times length plus width equals 20. This means that the sum of one long side and one short side must always be 10.
Now for modeling the area function, well, we need to see the relationship of variables. If we solve for W in terms of L, which is W equals 10 minus L, the area, which is A, is calculated by multiplying the length by the width. This gives us A of x equals L times 10 minus L equals 10L minus L squared. So then we have obtained a quadratic function which give us in the graph give us an inverted parabola. Now the analysis of the parabola, well, we can see the maximum area, which is L equals 5, as the length approaches 5, the area grows, and after exceeding 5, the area decreases. And now into the optimization process. Well, the first step was to find the derivative of the function to find the critical points. The second step was to set the derivative to 0 to find the maximum. And the third step was to verify, to calculate the corresponding heights. The ideal shape, well, it was the 5 times 5 square calculations demonstrate that for a fixed perimeter, the rectangular shape that encloses the maximum area is always a square. In our case, the dimensions were 5 blocks times 5 blocks. The total area was 25 square units, and in any other combination, such as 4 times 6 or 3 times 7, will result in less useful space.
To verify our solution, we compare different rectangles that all have the same perimeter of 20 units. Using the perimeter formula, P equals 2 times L plus 2 times W. We tested several pairs of dimensions. A rectangle measuring 1 by 9 has an area of 9 square units. A rectangle measuring 3 by 7 has an area of 21 square units. A rectangle measuring 4 by 6 has an area of 24 square units. But when both dimensions are 5 units, the area becomes A equals 5 times 5 equals 25. This is the largest area in the table. When the dimensions become less balanced again, such as 8 by 2 the area decreases to 16 square units. These results show that with a fixed perimeter, the maximum area is obtained when the rectangle is actually a square. This problem shows how mathematics can help us find the most efficient solution under a restriction. In this case, the restriction was having only 20 fence sections available using the perimeter condition 2L plus 2W equals 20. We express the area using only one variable and obtain the function a of L equals 10L minus L squared. Since this is a quadratic function that opens downwards, it has a maximum value. That is to say, that by finding its vertex, we determine that the maximum area occurs when L equals 5. Since the rectangle must satisfy the perimeter condition, the width is also 5 units. The maximum area is so the maximum area will be A equals 25. So the optimal dimensions are 5 units by 5 units, creating a square with an area of 25 square units. Uh, so this example demonstrates how optimization can be applied to practical situations, including construction, design, and games, where resources are limited and efficiency is very important. Thank you.